There is a place in the northern Rocky Mountains where the ground itself seems to be breathing, slow and warm. And lately, scientists who have spent entire careers listening to it say the rhythm of that breath has started to change in ways their instruments have never quite recorded before. Welcome back to Pale Blue Drift. If you are new here, let me tell you gently what this is, because it matters for how you should listen tonight. This channel exists for the hours when your mind is tired but still turning, still curious, still reaching for something to hold on to as the day loosens its grip on you. We take long, unhurried journeys through space and Earth and the quiet mechanics of the natural world, not to alarm you, but to give your thoughts somewhere calm and vast to drift while your body finally lets go. So if your eyelids grow heavy before this is finished, that is not a problem to solve. That is simply the story doing exactly what it was built to do. Tonight we are staying much closer to home than we sometimes do. We are not looking outward toward some distant star. We are looking down, into the ground itself, into a stretch of wilderness in Wyoming that most visitors know only as a place of geysers and hot springs and wandering bison, but which scientists have quietly understood, for decades now, to be something far stranger sitting just beneath that peaceful surface. Yellowstone is not simply a park. It is the visible skin stretched over one of the largest volcanic systems on the entire planet. And right now, in recent seismic records, researchers have been watching patterns of activity shift in ways that have made even experienced monitoring teams choose their words with unusual care. Let's walk into this slowly, the way we always do, because the real story here is far more interesting and far more honest than any single dramatic headline could capture on its own. To understand what is happening beneath Yellowstone today, you first have to understand what is actually sitting underneath it. And I want you to let this settle fully before we go any further, because the scale of it is genuinely difficult for the human mind to hold comfortably. Yellowstone sits above what geologists call a hotspot, an unusually persistent plume of heat rising up from deep within the Earth's mantle, far below the rigid, moving plates that make up the planet's outer shell. This heat has been rising in roughly the same place for millions of years, but the plate above it, the North American plate, has been slowly drifting across it the entire time, like a sheet of ice being dragged slowly over a lit candle. That is why, if you travel southwest from Yellowstone across Idaho, you can trace an entire trail of older, extinct volcanic calderas, a scar left behind by this same hotspot, sitting quietly beneath ground that is now peaceful, cooled, and long since finished with its violent chapter. Yellowstone itself is simply where that ancient trail of heat currently happens to sit, at this exact point in an extraordinarily slow, ongoing geological journey. Beneath the park, that rising heat has created something almost impossible to picture cleanly, a vast reservoir of partially molten rock, sitting many miles below the surface, kept liquid enough by heat and pressure to shift and move, though far too thick and crystal-laden in most places to behave like the flowing lava you might picture from a more ordinary volcano. Scientists have mapped this reservoir using seismic waves, essentially listening to how vibrations from distant earthquakes travel differently through molten rock than through solid stone, the way you might tap on a wall and listen for a hollow section behind it. What they have found is a magma system stretching for dozens of miles beneath the surface, layered in at least two major zones, an upper chamber closer to the surface, and a deeper, even larger one further below it, feeding the system from beneath. This is the engine responsible for everything visitors associate with Yellowstone, the geysers that erupt on their strange, private schedules, the hot springs painted in impossible colors by heat-loving microbes that thrive nowhere else on Earth in such variety, the gentle, constant warmth rising up through certain patches of ground, even in the depths of a Wyoming winter. All of it is the surface expression of that deep, patient heat, venting quietly, harmlessly, through thousands of small features scattered across the park, the way steam escapes gently from a covered pot long before the water beneath it ever comes close to a genuine boil. And for most of human history, and certainly for the entire span of recorded observation, that is almost exactly what Yellowstone has been. A vast, deeply hot system, venting its pressure steadily and safely through countless small features, monitored today by one of the most sophisticated volcanic observation networks anywhere on the planet. That network is where tonight's real story actually begins, because what has scientists choosing their words carefully lately is not some sudden, singular event. It is a pattern, gathered slowly, patiently, across recent seismic records, showing shifts in the timing and character of small earthquakes beneath the park that some researchers say do not quite match the typical rhythm the system has followed in the decades since modern monitoring began. Yellowstone experiences earthquakes constantly. This is not new, and it is not, on its own, alarming. The park typically records between 1 and 2,000 small earthquakes every single year, the overwhelming majority of them far too small to be felt by anyone standing above them, registering only on the sensitive instruments buried throughout the region specifically to catch them. Most of these earthquakes occur in what seismologists call swarms, clusters of smaller quakes occurring close together in time and location, often triggered simply by fluid movement deep underground, water and gas shifting slowly through cracks in the rock, adjusting pressure the way a house settles quietly on its foundation over the years. For most of Yellowstone's monitored history, these swarms have followed patterns familiar enough that scientists could describe them almost the way you might describe a person's normal resting heartbeat. Not perfectly identical every time, but recognizable, falling within an expected range of behavior. What has drawn careful attention recently is a stretch of activity where certain swarms have shown durations, depths, or migration patterns. The way a cluster of small quakes gradually moves through the ground over hours or days, that sits slightly outside that familiar historical range, prompting monitoring teams to look more closely, gather more data, and importantly, say clearly and specifically what they do and do not yet know. I want to be very careful and very honest with you here, because this is exactly the point where so many stories about Yellowstone quietly slip away from what the evidence actually supports into something far more dramatic and far less true. The scientists who study this volcanic system every single day, people who have devoted entire careers to reading its seismic heartbeat, have been consistent and clear in their public statements. Unusual patterns in earthquake swarms are not, by themselves, evidence of an approaching eruption. They are evidence that the system beneath Yellowstone is dynamic, active, and constantly adjusting, which is precisely what a living volcanic system does, whether or not anything dramatic is ever going to follow from it. The distinction matters enormously, and it is worth sitting with for a moment, because it is the difference between genuine scientific caution and manufactured alarm. A doctor noticing an unfamiliar pattern on an otherwise healthy patient's heart monitor does not immediately declare a crisis. They pay closer attention. They gather more readings. They compare the pattern against a much larger history of what that same heartbeat has done before, under all kinds of ordinary circumstances, most of which turn out to explain the change without anything serious being wrong at all. That is precisely the posture Yellowstone's monitoring teams have taken toward these recent shifts: patient, attentive, unwilling to declare anything beyond what the data can actually support in either direction. And there is a very good reason for that careful patience, beyond simple scientific caution. Yellowstone possesses one of the densest, most sophisticated volcanic monitoring networks of any system on the planet, precisely because of how much attention it has justifiably received for decades. Dozens of seismometers are buried throughout the region, continuously recording every tremor, no matter how small. Networks of GPS stations measure the ground itself, tracking whether the surface above the magma system is slowly rising, slowly sinking, or holding steady. Changes measured not in feet, but in millimeters, small enough to require satellite precision to notice at all. Additional instruments monitor the chemistry and temperature of gases escaping from the ground in specific locations, watching for shifts in composition that, in other volcanic systems around the world, have sometimes preceded periods of increased activity. All of these instruments feed continuously into a monitoring effort run jointly by government geological agencies and university researchers, producing a real-time picture of the system's behavior that updates constantly, publicly available for anyone patient enough to read through it. This is not a system being watched casually, or infrequently, or with any gaps of ignorance waiting to be exploited by surprise. It is, quite genuinely, one of the most closely observed patches of ground anywhere on Earth, precisely because everyone involved understands exactly what could theoretically be at stake if the deeper system beneath it ever did begin moving toward a genuinely different kind of behavior. And this is where the honest, careful shape of the recent story actually sits. The monitoring teams have not raised the volcanic alert level for Yellowstone. That alert level, a formal, carefully defined classification system used across volcanic observatories, remains, as it has for years, at its lowest possible setting, the same level assigned to a system considered to be in typical background behavior. Ground deformation measurements, the slow rise or fall of the surface above the magma system, have shown patterns consistent with historical norms, not signs of significant new pressure building toward the surface. Gas emissions have not shown compositional shifts of the kind associated with rising magma approaching more shallow depths. What has changed, specifically, carefully, is the character of certain seismic swarms, patterns interesting enough, and different enough from decades of prior baseline data, that they have become worth genuine scientific attention, worth careful modeling, worth ongoing observation as more data continues to accumulate in the weeks and months ahead. That is a meaningfully different statement than an approaching eruption, and it is worth letting that distinction settle fully into your mind before we go any further into what these swarms might actually represent. Because underneath all of this, there is something genuinely beautiful happening, something worth appreciating fully even in its uncertainty. What scientists are witnessing, in real time, through instruments sensitive enough to catch the smallest imaginable shifts in the Earth's crust, is a living volcanic system continuing to breathe, continuing to adjust, continuing to move fluid and heat and pressure through channels carved slowly over millions of years, exactly the way it has behaved for as long as anyone has been patient enough to listen closely to it. The fact that we can watch this happen at all, in this much detail, updated in something close to real time, represents an extraordinary achievement of patient scientific effort stretched across generations of researchers who came before the ones currently on watch tonight. Let your mind rest for a moment on the sheer scale of patience this kind of monitoring requires. Instruments have been recording data beneath Yellowstone continuously for decades, accumulating an enormous historical baseline of exactly what normal behavior looks like, swarm after swarm, season after season, so that when something genuinely different eventually does appear in the data, researchers have a real, solid foundation to measure it against rather than simply guessing at what might be unusual. That baseline is precisely what allows scientists to say, with genuine confidence, when a pattern falls comfortably within known historical behavior, and precisely what allows them to notice, carefully and honestly, when something begins to sit slightly outside of it. It helps, too, to understand what this system has actually done in the deep past, because the word volcano tends to summon a very particular image in most people's minds. A tall, cone-shaped mountain, smoke curling from its peak, lava spilling dramatically down its sides. Yellowstone looks nothing like that, and there is a specific, important reason for it. The kind of eruption this system is capable of producing does not build a mountain at all. It does the opposite. It creates a vast depression in the ground called a caldera, formed when an eruption is so large, and empties so much material from the magma chamber below, that the ground above it loses its support and collapses gently downward, leaving behind a wide, shallow basin rather than a rising peak. Yellowstone has done this 3 times in its known history, spaced across roughly 2 million years, each event separated from the last by many hundreds of thousands of years of quieter, ordinary volcanic behavior in between. The most recent of these 3 calderas formed around 630,000 years ago, and it is the very same depression that today makes up much of the landscape visitors walk through without ever quite realizing its true shape, because it is so large, several dozen miles across, that it simply looks like ordinary rolling terrain rather than the rim of an ancient volcanic basin. You could stand at certain overlooks within the park and be looking directly across the floor of that ancient caldera without any obvious visual cue announcing what you are seeing, the scale of it too vast for the human eye to register as a single connected shape. Since that last major event, Yellowstone has not been dormant. It has continued to produce smaller eruptions, dozens of them, spilling thick, slow-moving lava flows across parts of the caldera floor over tens of thousands of years, the most recent occurring roughly 70,000 years ago. These were still significant volcanic events by ordinary standards, but nothing resembling the scale of the caldera forming eruptions that came before them. This pattern, long stretches of smaller, localized activity, punctuating the much longer intervals between major caldera-forming events, is exactly the kind of behavior researchers expect a system like this to continue exhibiting for a very long time yet, likely tens of thousands of years at minimum, based on everything currently understood about how these systems recharge and behave over geological timescales. That is worth repeating clearly, because it directly shapes how the current seismic activity should actually be understood. The overwhelming scientific consensus, based on decades of careful study of the magma system's current size, composition, and behavior, is that there is no evidence Yellowstone is moving toward another caldera forming eruption on anything resembling a near-term timescale. The kind of preparation such an event would require: enormous volumes of fresh, gas-rich magma accumulating rapidly in the shallow chamber, sustained and dramatic ground uplift across the caldera, major shifts in gas chemistry consistent with magma rising toward the surface, simply is not present in the current data, regardless of how the recent earthquake swarms are ultimately explained. What the current instruments are watching instead sits at a far smaller, far more ordinary scale, the kind of activity this system exhibits constantly, in between its rare major eruptions, as fluids shift, as small pockets of gas and hot water migrate through fractured rock, as pressure adjusts gradually across a vast underground plumbing system that has been quietly rearranging itself for hundreds of thousands of years. Even Yellowstone's most dramatic recent seismic event on record, a powerful earthquake in 1959 that triggered a landslide and altered the timing of dozens of the park's geysers overnight, was not connected to any volcanic eruption at all. It was a fault rupture, a shift along one of the many geological fractures running through the region, a reminder that this landscape carries multiple overlapping sources of natural activity, only some of which are directly tied to the magma system itself. This is precisely the kind of nuance that gets lost whenever this topic travels quickly across headlines, and it is worth sitting with carefully tonight. An earthquake swarm beneath Yellowstone can be genuinely unusual, genuinely worth careful scientific attention, and still fall entirely within the range of ordinary fault activity or fluid movement that has nothing whatsoever to do with an approaching eruption. Distinguishing between these possibilities is exactly the painstaking work currently underway, comparing seismic wave patterns against decades of historical data, checking ground deformation measurements for any hint of unusual uplift, monitoring gas chemistry for any shift that might suggest magma migrating toward shallower depths. So far, according to the researchers closest to this data, The broader picture continues to point toward ordinary hydrothermal and tectonic behavior, rather than anything suggesting deeper volcanic unrest. We are going to spend the rest of this evening walking through exactly what those recent seismic patterns actually looked like, how researchers went about analyzing them, what the leading scientific explanations currently are for what might be causing this particular shift, and what history, both recent and ancient, actually tells us about how systems like this one tend to behave when their underlying rhythms begin to change. None of it demands fear. All of it deserves genuine, patient curiosity, the same quality of attention the scientists themselves have been bringing to this question, night after night, for as long as the instruments have been listening. For now, let the shape of it settle. A vast, ancient reservoir of heat, sitting patiently beneath a landscape most people only ever visit for its geysers and its wildlife. A monitoring network built across decades, listening constantly, carefully, for exactly this kind of shift. And a recent stretch of seismic activity, genuinely unusual against that long historical baseline, currently being studied with exactly the kind of careful, unhurried attention that good science always demands, regardless of how dramatic the surrounding conversation about it might sometimes become. The ground beneath that ancient landscape is still breathing tonight, exactly as it has for longer than any human record has existed to describe it. And somewhere in that patient, ongoing rhythm, there is still far more waiting to be understood than there is anything yet worth being afraid of. Exactly what those recent seismic patterns actually looked like. But before we get to the numbers themselves, it helps to sit for a moment with the surface of the park itself. Because long before any seismometer ever registered anything unusual underground, the first hints that something in this system was shifting have historically come from something far simpler and far more visible: the behavior of the geysers and hot springs that visitors walk past every single day. Yellowstone is home to more than half of all the geysers on the entire planet, a genuinely staggering concentration of a phenomenon so rare that most countries have none at all. Each one is, in its own quiet way, a kind of natural pressure gauge, a narrow plumbing system running deep underground, filled with water heated far past its normal boiling point by the rock surrounding it, held from actually boiling only by the sheer weight of water and pressure sitting above it, until eventually that pressure gives way all at once, and the whole column erupts upward in a release that can last seconds, or, in some of the park's most famous features, several minutes at a time. The timing of these eruptions is not random, and it is not fixed either. It reflects, quite precisely, the underlying plumbing and heat conditions feeding each individual geyser, which means that when conditions shift underground, even slightly, the surface behavior of these features often shifts along with them, sometimes before anything else about the system becomes noticeable at all. This is exactly why geologists pay such close attention to something that might otherwise sound almost whimsical: the changing schedule of a famous geyser's eruptions. Old Faithful, the park's most recognizable feature, has never actually erupted on a perfectly fixed schedule, despite its name suggesting otherwise. Its interval between eruptions has drifted gradually over the decades, lengthening somewhat compared to historical records from many decades ago, a change researchers generally attribute to gradual, ordinary shifts in the underground plumbing feeding it, deposits of mineral-rich sediment slowly narrowing certain channels, small earthquakes occasionally opening or closing others. This kind of slow drift is considered normal, expected, and not a cause for concern on its own. What draws far more careful attention is something different: a geyser or hot spring changing its behavior abruptly, over the course of days or weeks rather than years, especially when that change coincides with a broader pattern of shifting seismic activity nearby. In recent seasons, park geologists have documented exactly this kind of behavior in a handful of features scattered across different geyser basins, some hot springs shifting color as their temperature or chemistry changed, some previously quiet thermal features beginning to steam more actively, some smaller geysers altering their eruption intervals noticeably within a short window of time. None of this, taken individually, is alarming. Yellowstone's thermal features have always changed over time, sometimes dramatically, entirely independent of any broader volcanic unrest. An earthquake can shake loose a mineral blockage in an underground channel and instantly change a geyser's behavior permanently, the way it did to several features during that 1959 earthquake we discussed earlier. A shift in groundwater levels following an unusually wet or dry season can alter the temperature and pressure feeding a hot spring without anything happening deeper in the magma system at all. This is a genuinely dynamic, living landscape, constantly rearranging its own plumbing in small ways, most of which never connect to anything happening in the deep magma reservoir far below it. What makes the current stretch of observation different is not any single changed geyser or any single unusual hot spring. It is the fact that several independent lines of evidence, surface thermal changes, seismic swarm characteristics, and subtle shifts in specific monitoring stations, have been trending in a similar direction across a similar window of time, which is exactly the kind of coincidence that earns careful scientific attention rather than immediate alarm. Coincidence is not causation, and researchers are quick to say so publicly. But coincidence across multiple independent measurement systems is precisely the kind of signal that justifies closer, more detailed analysis rather than dismissal. This is a good moment to walk through exactly how scientists actually go about distinguishing between different possible causes of underground activity, because the process itself is a genuinely elegant piece of detective work, built from decades of refined technique. The first and most fundamental tool is the shape of the seismic waves themselves. Earthquakes caused by rock fracturing along a fault, the kind of ordinary tectonic activity found in mountain ranges all over the world, produce a very specific, sharp signature when recorded by a seismometer. A sudden, high-frequency burst of energy that fades relatively quickly. Earthquakes associated with fluid movement, water and gas shifting and pressurizing through cracks in volcanic rock, tend to look different, often longer in duration, sometimes containing a distinctive, lower-frequency rumble described by researchers as harmonic tremor, a signal that resembles a sustained hum more than a sharp crack. By carefully analyzing the shape of thousands of individual seismic events, researchers can build a detailed picture of what is actually happening underground, fluid movement versus simple rock fracture, without ever needing to see beneath the surface directly. The second major tool is location and migration. When researchers plot the location of every earthquake in a swarm over time, patterns emerge that tell their own story. A swarm that stays roughly fixed in one location, gradually decreasing in frequency and size, typically represents rock settling after an initial disturbance, releasing built-up stress until it reaches a new, stable equilibrium. A swarm that migrates steadily in one direction over hours or days, however, often indicates fluid actively moving through a network of cracks, pressure propagating outward as water or gas forces its way through progressively more distant sections of rock. This second pattern is watched with particular care in volcanic systems, because sustained fluid migration, especially if it appears to move toward shallower depths over time, can sometimes indicate magma itself beginning to move, rather than simply water or gas shifting through existing channels. It is important to say clearly that migration on its own, even migration toward shallower depths, does not necessarily mean magma is involved at all. Yellowstone's extensive hydrothermal system, the vast underground network of hot water and steam that feeds every geyser and hot spring in the park, is itself capable of producing exactly this kind of migrating seismic pattern as water shifts and boils, and refills through its own plumbing. Entirely independent of the magma reservoir sitting much further below it. Distinguishing between hydrothermal fluid movement and genuine magmatic movement requires additional evidence beyond seismic patterns alone, which brings us to the third major tool researchers rely on: ground deformation. Every few weeks, satellites orbiting overhead capture extraordinarily precise measurements of the exact elevation of the ground across the entire Yellowstone region, sensitive enough to detect changes measured in mere millimeters. This technique, called interferometric synthetic aperture radar, works by comparing radar signals bounced off the same patch of ground during different satellite passes, detecting even the smallest shifts in distance between the satellite and the surface below. Combined with a dense network of ground-based GPS stations providing continuous, real-time measurements at fixed points across the caldera, researchers maintain what amounts to a constant, extraordinarily precise map of whether the ground above the magma system is rising, falling, or holding steady. This measurement matters enormously because magma rising toward the surface physically pushes the ground above it upward as it accumulates, a process that has been documented clearly in the lead-up to eruptions at volcanic systems around the world. Significant, sustained uplift, especially uplift that accelerates over time and concentrates specifically above the shallow magma chamber, is one of the clearest and most reliable warning signs available to volcanologists anywhere. Yellowstone's ground deformation record, closely tracked across the recent period of unusual seismic activity, has continued to show movement broadly consistent with decades of historical background behavior, the caldera floor rising and falling gently across different sections in patterns that match what researchers have observed for years, rather than the kind of sustained, accelerating, spatially concentrated uplift that would raise serious concern about magma actively approaching the surface. The fourth and final major tool involves gas chemistry, sampled directly from specific vents and fumaroles scattered across the park, where volcanic gases naturally escape from deep underground. As magma rises toward the surface, it releases gases in a fairly predictable sequence, carbon dioxide typically escaping first from greater depths, followed later by sulfur dioxide as magma approaches much shallower levels, closer to where it could eventually erupt. By regularly sampling and analyzing the exact chemical composition of gases escaping from monitored vents, researchers can watch for this specific sequence beginning to appear, a genuine, physical signature of magma actively migrating upward through the crust. Current gas monitoring data from Yellowstone's fumaroles has not shown this kind of shift, the chemical composition remaining broadly consistent with typical, long-term hydrothermal system behavior rather than any pattern suggesting magma moving toward shallower depths. Taken together, these four independent lines of evidence, seismic wave shape, earthquake migration patterns, ground deformation measurements, and gas chemistry, form the actual scientific basis researchers use to evaluate exactly what is happening beneath Yellowstone at any given moment. And it is worth appreciating just how much careful, patient technical work sits behind every public statement issued about the park's current status. When monitoring teams describe recent activity as unusual but not indicative of increased volcanic hazard, that statement is not a guess or a reassurance offered simply to prevent panic. It reflects a detailed, ongoing cross-analysis of multiple independent measurement systems, each one capable of catching a different kind of warning sign, none of which have yet aligned in a way that would suggest anything beyond the system's normal, dynamic, ever-shifting background behavior. And yet, the fact that this recent swarm activity has drawn this much careful attention at all tells you something worth sitting with honestly. It is genuinely unusual, measured against decades of prior data, unusual enough that researchers have chosen to say so publicly, unusual enough to justify additional instrumentation being deployed to specific areas of the park, unusual enough that follow-up studies are actively underway right now, tonight, as this recording plays quietly in whatever room you happen to be resting in. Science does not require certainty in order to justify attention. It only requires a genuine deviation from an established pattern, And that is precisely what has been observed here. A deviation still being carefully measured, still being patiently explained, one data point at a time, by people who understand exactly how much responsibility comes with getting an answer like this right. There is something worth appreciating in this kind of patient, layered uncertainty, rather than something worth fearing. The ground beneath Yellowstone has been speaking, in its own slow language of tremors and gas and gently shifting elevation, for far longer than any instrument has existed to properly listen. What has changed recently is not necessarily the ground itself, but simply how closely and how carefully we have finally become capable of listening to it. It helps, too, to look back at how the system has behaved during previous periods of heightened attention, because Yellowstone has been here before, in its own way, more than once. In 2010, the park experienced one of its largest recorded earthquake swarms, more than 2,000 small quakes occurring over the span of about a month beneath the Yellowstone Lake area, drawing significant public attention and no small amount of concern at the time. Researchers studied that swarm closely, tracking its migration, its depth, its relationship to nearby fault structures, and ultimately concluded it represented a normal, if unusually large, release of tectonic stress along an existing fault system, not any indication of magma movement. The swarm gradually tapered off over the following weeks, exactly as models predicted for this kind of tectonic release, and the park's broader monitoring data showed no lasting change in its underlying volcanic hazard status. A similar pattern played out again in 2017, when another significant swarm, this time located beneath the northwestern section of the park, produced several thousand small earthquakes over a period of a few months, at the time becoming one of the longer sustained swarms in the modern monitoring record. Once again, careful analysis of wave patterns, migration behavior, and accompanying ground deformation data pointed toward fluid readjustment within existing fracture networks rather than magma movement, and the swarm eventually settled back toward the park's typical background seismic rate. These examples matter because they establish something important about how this system tends to behave, and how researchers have learned to interpret its signals over repeated cycles of heightened activity followed by a return to baseline. Large, attention-drawing swarms are not new. They have happened before, been studied thoroughly, and so far, without exception, ultimately been explained by processes well short of any genuine volcanic escalation. This does not guarantee that every future swarm will resolve the same way, and researchers are careful never to promise that outright. But it does provide a meaningful, evidence-based context for understanding why the current activity, however unusual its specific characteristics, has not yet crossed into a category the monitoring teams consider genuinely concerning. One particular thermal feature is worth mentioning by name here, because its recent history illustrates exactly the kind of surface behavior scientists watch closely without necessarily treating as alarming. Steamboat Geyser, located in the park's Norris Geyser Basin, holds the distinction of being the tallest active geyser currently found anywhere on Earth, capable of launching water higher than 300 feet into the air during its largest eruptions. For decades, Steamboat's eruptions were exceedingly rare and unpredictable, sometimes going years, occasionally even decades, between major eruptions, its underlying plumbing apparently requiring long, patient stretches of pressure buildup between each dramatic release. Then, beginning in 2018, Steamboat's behavior shifted dramatically, entering an active phase during which it erupted repeatedly, sometimes just days or weeks apart, a level of activity unlike anything recorded in the geyser's documented history. This shift drew significant scientific interest, and researchers studied it carefully, monitoring nearby seismic activity, ground temperature, and groundwater conditions in the surrounding basin to understand what had changed. The leading explanation that emerged connected the shift to changes in the local hydrothermal plumbing, following a period of increased snowmelt and groundwater recharge in the years leading up to the reactivation, altering the underground pressure and temperature balance feeding the geyser's conduit, rather than any deeper connection to the magma system far below. Steamboats' dramatically increased activity continued for several years afterward, a genuinely remarkable natural event, and a clear demonstration of how significantly a single thermal feature's behavior can shift due to processes confined almost entirely to the shallow hydrothermal system, without that shift reflecting anything happening in the much deeper magma reservoir. Examples like Steamboat's reactivation are part of why researchers are so careful to separate hydrothermal activity from volcanic activity when discussing changes at Yellowstone, even though both processes are ultimately powered by the same underlying source of heat far below. The hydrothermal system, the vast network of hot water, steam, and dissolved minerals filling cracks and reservoirs throughout the upper few miles of crust beneath the park, behaves according to its own complex, sensitive rules, responsive to seasonal snowmelt, rainfall, small earthquakes, and gradual mineral deposition, narrowing or widening individual channels over time. It can produce genuinely dramatic, visible changes at the surface, new geysers appearing, old ones falling silent, ground temperatures shifting noticeably in specific areas, entirely independent of whether the deep magma chamber below is doing anything unusual at all. This layered structure, a deep, slow-moving magma reservoir feeding a far more responsive, changeable hydrothermal system sitting above it, is precisely what makes evaluating Yellowstone's current activity such a genuinely careful, multidisciplinary task. A change at the surface does not automatically mean a change deep below, and a change deep below would not necessarily announce itself through the surface immediately or obviously. It requires exactly the kind of patient, cross-referenced analysis we have spent this evening walking through. Seismic patterns compared against historical baselines, ground deformation tracked continuously by satellite and GPS, gas chemistry sampled and resampled at monitored vents, surface thermal features documented carefully season after season, each measurement serving as one piece of a much larger, slowly assembling picture. That picture, as it currently stands, continues to point toward a system behaving in ways broadly consistent with its long-documented history, adjusting, shifting, occasionally surprising even the researchers who know it best, but not yet showing the specific, convergent signs that would indicate a genuine escalation toward increased volcanic hazard. The story is not finished, and the researchers watching it most closely would be the first to say so themselves, continuing to gather data, continuing to refine their models, continuing to treat this ancient, patient system with exactly the careful attention it has always deserved, long before any recent swarm ever made headlines at all. It is worth stepping back now for a while, from the instruments and the swarms and the careful measurements, and letting your mind drift outward toward the wider context all of this sits inside, because Yellowstone is not an isolated curiosity. It is one member of a much larger family of volcanic systems scattered across the planet, and understanding how it compares to its relatives, and how it fits into the broader story of how our world watches its own volcanic activity, makes the careful, patient monitoring happening there right now feel even more remarkable. Most of the volcanoes people picture when they hear the word sit along a rough, broken ring circling the Pacific Ocean, a vast boundary where several of the Earth's major tectonic plates grind against and slide beneath one another, generating enormous amounts of heat and pressure as they do. This region has earned the informal name the Ring of Fire, and it is home to the overwhelming majority of the world's active volcanoes, along with the greatest concentration of significant earthquakes recorded anywhere on the planet. Japan sits along it. Indonesia sits along it. The western coastline of North and South America sits along it, From the volcanic peaks scattered through the Pacific Northwest down through Mexico and Central America, and into the towering, still active volcanoes lining the spine of the Andes. Yellowstone, interestingly, does not sit along this ring at all. It sits deep in the interior of North America, far from any plate boundary, which is part of what makes its existence so scientifically fascinating in the first place. Its heat source is not generated by two plates colliding or sliding past each other. It is generated by that deep, stationary mantle plume we discussed earlier, a hotspot rising from far below the moving plate above it, essentially unrelated to the plate boundary processes responsible for the vast majority of the world's volcanic activity. This makes Yellowstone something of a rare category unto itself, one of only a small handful of continental hotspot systems capable of producing the kind of massive caldera forming eruptions we discussed in our first part together tonight. There is another well-known hotspot system many listeners will already be familiar with, sitting in the middle of the Pacific Ocean rather than the middle of a continent, responsible for building the Hawaiian island chain over millions of years as the Pacific plate slowly drifted across the same stationary plume of rising heat, one island forming, then drifting away from the hotspot as a new one began forming behind it, leaving an entire chain of islands stretching across the ocean like footprints marking the plate's slow journey. Hawaii's volcanoes behave very differently from Yellowstone's system, however, producing the more familiar image of flowing lava and gradually built shield volcanoes, because the magma feeding them is thinner, less viscous, and considerably lower in dissolved gas than the thicker, more gas-rich magma sitting beneath Yellowstone's crust. This difference in magma chemistry is precisely why Hawaii's eruptions tend to be relatively gentle, effusive events, while Yellowstone's rare major eruptions have historically been explosive on a scale almost impossible to compare directly to anything else on the planet. To understand exactly how significant that scale actually is, it helps to look at the handful of other volcanic systems on Earth capable of producing eruptions in the same general category, sometimes referred to using a scale developed specifically to compare the size of explosive eruptions, ranking them from the smallest, most common events up through the very largest, rarest category, one that Yellowstone's three major historical eruptions all belong to. The most recent eruption anywhere on Earth confidently placed in that same largest category occurred roughly 74,000 years ago, at a volcanic system called Toba, located on the island of Sumatra in Indonesia. That eruption is estimated to have ejected an amount of volcanic material so large that some researchers have connected it to a period of significant global cooling in the years immediately following, based on evidence of ash deposits found scattered across a remarkably wide portion of South Asia. Layers of fine volcanic glass still detectable in soil samples taken from locations thousands of miles from the eruption site itself. The exact scale of Toba's global climate impact remains an active area of scientific debate, with some researchers arguing the cooling effect was more moderate and localized than early estimates suggested. But there is no debate at all about the eruption's sheer physical scale, producing a caldera roughly 60 miles long, among the largest volcanic depressions found anywhere on the planet today. Yellowstone's own largest eruption, the one that formed its oldest and most massive caldera roughly 2.1 million years ago, is estimated to have been comparable to, and by some measurements even larger than, the Toba eruption, making it one of the most significant volcanic events in the entire geological record of our planet. Ash from that ancient Yellowstone eruption has been found preserved in sediment layers across a huge stretch of what is now the central United States, evidence of just how far-reaching an eruption of this scale can be, even without any of the fine, complex modeling tools modern researchers now have available to study such events. It is genuinely important to sit with the timescale involved here, because it is the piece of this story most frequently lost entirely whenever Yellowstone becomes a subject of dramatic headlines. That massive eruption occurred 2.1 million years ago. The second, still enormous but noticeably smaller eruption occurred 1.3 million years ago. The third and most recent occurred 630,000 years ago. These intervals, roughly 800,000 years, then roughly 700,000 years, are themselves part of what researchers study carefully when trying to estimate anything about the system's future behavior, though they are always quick to caution that a sample size of only 2 intervals is far too small to treat as any kind of reliable, predictable schedule. Geological systems like this one do not operate on the kind of neat, repeating calendar that headlines sometimes imply. They are governed by the slow accumulation of specific physical conditions, sufficient volume of eruptible magma, sufficient dissolved gas content, sufficient pressure building within a chamber that has grown large enough and shallow enough to eventually fail catastrophically. Conditions that current data shows the shallow magma chamber beneath Yellowstone has not yet come close to reaching. Recent detailed studies mapping the composition of Yellowstone's shallow magma reservoir have found that the vast majority of material within it currently exists in a mostly solid, crystalline state, with only a relatively small percentage existing as fully molten, eruptible liquid, scattered in pockets throughout the much larger crystal framework, rather than forming one enormous, continuous body of liquid rock ready to erupt. This finding, published following careful seismic imaging studies of the reservoir, was considered genuinely reassuring by much of the volcanological community, because it demonstrated clearly that the system, in its current state, is nowhere near having accumulated the kind of large, connected, predominantly liquid magma body, historically associated with the lead up to a major caldera forming eruption anywhere in the geological record. This is precisely the kind of deep, structural evidence that sits underneath the confident, careful public statements researchers continue to make about Yellowstone's current status, even while closely monitoring the recent unusual seismic patterns we discussed earlier. The system's deep architecture, studied through years of painstaking seismic imaging, gives no indication of approaching a major eruption on anything resembling a near-term timescale, regardless of how the current swarm of smaller earthquakes and shifting hydrothermal features ultimately gets explained. These are, in a very real sense, 2 separate layers of the same story, a slow, deep architecture that changes across hundreds of thousands of years, and a much faster, shallower layer of hydrothermal and tectonic activity that shifts across days, weeks, and months, occasionally producing exactly the kind of attention-drawing swarm currently being studied, without that faster layer necessarily reflecting anything happening within the much slower, deeper one below it. Understanding this distinction is, in many ways, the entire key to holding this story calmly rather than fearfully. It would be entirely reasonable to feel a flicker of unease upon hearing that Yellowstone's earthquake patterns have shifted into something genuinely unusual, especially with a system this historically significant sitting behind those numbers. But that unease softens considerably once you understand just how many independent layers of evidence researchers actually have available, and just how consistently, across every one of those layers, decades of careful measurement continue to point toward a system behaving dynamically, adjusting constantly, occasionally surprising even its closest observers, and yet, so far, remaining firmly within the range of behavior this system has quietly, patiently exhibited for as long as anyone has been capable of measuring it in this much careful detail. There is a particular kind of comfort available in appreciating just how much quiet, dedicated human effort sits behind a system like this being watched this carefully. Researchers rotate through remote monitoring stations scattered across some of the most rugged terrain in the American West, maintaining sensitive instruments through brutal winters and scorching summers, year after year, decade after decade, so that a shift in the ground's rhythm, however small, however subtle, does not go unnoticed. Universities and government agencies coordinate constantly, sharing data, comparing models, publishing findings openly for other scientists around the world to review and challenge and refine further. It is, in its own way, one of the quieter, more patient acts of collective human care currently underway anywhere on the planet. An entire community devoted to listening closely to a landscape most people only ever think about during a brief summer vacation, making sure that if this ancient, patient system ever does begin genuinely shifting towards something different, there will be people ready, watching, prepared to notice it as early as humanly possible. For tonight, that patient watching continues exactly as it has for years. Instruments recording quietly in the dark, satellites passing silently overhead, gas samples being collected carefully from steaming vents, scattered across a landscape settling slowly into its own long, unhurried winter or summer, whichever season currently holds it. Yellowstone is far from alone in receiving this kind of careful, continuous attention. Around the world, a small number of other volcanic systems capable of producing similarly enormous eruptions are being watched with comparable dedication, and it is worth knowing a little about them, because their stories rhyme closely enough with Yellowstone's own that they offer useful, calming context. In southern Italy, near the city of Naples, sits a volcanic region called Campi Flegrei, a wide, low caldera formed by eruptions in the ancient past, now home to hundreds of thousands of people living directly across its gently sloping terrain. Campi Flegrei has experienced its own periods of significant unrest in recent decades, including episodes of measurable ground uplift and increased seismic activity that, in the 1980s, actually forced the temporary evacuation of part of one coastal town as researchers monitored the situation closely. That uplift eventually stabilized without producing an eruption, and the region has continued to experience intermittent periods of renewed unrest since, each one studied with the same careful, multi-layered approach we described earlier: seismic analysis, ground deformation tracking, and gas chemistry sampling, each episode so far settling back toward quieter background behavior after periods of heightened activity. Though Italian volcanologists continue to monitor the system with particular vigilance, given how densely populated the surrounding area is. In California, another well-known caldera called Long Valley has drawn similar scientific attention since the early 1980s, when a swarm of earthquakes beneath the region, combined with measurable ground uplift, prompted the United States Geological Survey to issue a formal notice of potential volcanic hazard, the first time such a notice had been issued in the country's history. That period of unrest, much like the episodes at Campi Flegrei, eventually settled without producing an eruption, though Long Valley has continued to show intermittent signs of activity in the decades since, remaining one of the most closely monitored volcanic systems in North America alongside Yellowstone itself. These examples matter because they demonstrate something important about how volcanic systems capable of large eruptions actually tend to behave across human observable timescales. Periods of measurable unrest, sometimes quite significant unrest, are not unusual for systems like this. They occur periodically, draw careful scientific attention exactly as they should, and in the overwhelming majority of documented cases across the modern monitoring era, resolve back toward quieter background behavior without producing any eruption at all. This is not a guarantee about what any particular episode of unrest will ultimately do, and researchers are always careful never to offer that kind of promise, but it is a meaningful, evidence-based pattern worth holding onto, drawn not from a single system's history, but from comparing multiple similar systems being watched closely around the world. There is also a broader, global effort worth knowing about, a coordinating body that tracks volcanic activity at thousands of sites across every continent, maintaining a continuously updated public record of eruptions, unrest, and monitoring status for volcanoes everywhere, allowing researchers studying any single system, Yellowstone included, to draw on patterns and lessons learned from volcanic behavior observed anywhere else on the planet. This kind of shared, collaborative global effort means that no single monitoring team is ever working from a blank slate. Every unusual seismic swarm, every shift in ground deformation, every change in gas chemistry observed at Yellowstone gets interpreted against a backdrop of decades of comparable observations gathered from volcanic systems scattered across dozens of countries. An enormous, quietly accumulated body of collective human understanding, built specifically so that moments like this current period of unusual activity can be evaluated with as much context and as much calm, careful perspective as possible. There is something worth lingering on in these last few quiet minutes before we let this particular thread of the story rest, about why places like Yellowstone hold such a persistent grip on the human imagination in the first place. Part of it is simply scale, the way a system capable of altering global climate, of leaving ash layers detectable across an entire continent millions of years later, forces our minds to stretch a little beyond their ordinary, comfortable sense of what nature is capable of. But part of it, too, is something quieter and more personal, the strange, unsettling knowledge that something this old, this vast, this patient, is sitting directly beneath a landscape most people associate with something as gentle as a family vacation. Wandering boardwalks past bubbling mud pots and photographing elk grazing in open meadows, entirely unaware, most of the time, of the scale of what lies beneath their boots. That contrast, the surface calm and the deep, ancient power sitting quietly underneath it, is part of what makes this story so compelling to sit with at night, when the mind is finally quiet enough to hold something this large without immediately reaching for anxiety instead of wonder. The honest, evidence-based version of this story does not need exaggeration to hold your attention. It only needs the space to unfold slowly, layer by layer, exactly the way the researchers themselves have spent their careers learning to read it, patiently, carefully, one measurement at a time, letting the ground speak in its own unhurried language rather than demanding it explain itself all at once. The ground continues its ancient, ongoing conversation with the researchers listening to it, a conversation that has been unfolding for millions of years, long before there was ever anyone capable of understanding a single word of what it was saying, and one that will likely continue unfolding for millions of years yet to come, regardless of how any single stretch of unusual activity within it eventually resolves. So let's bring all of that back down, gently, to exactly where things stand tonight, back to the specific stretch of unusual seismic activity we began this journey with. Because after everything we have walked through together, the deep history, the global comparisons, the careful layered science of how researchers actually tell these signals apart, it is worth returning one final time to the honest, current shape of what is actually happening beneath that quiet, steaming landscape right now. The monitoring teams responsible for Yellowstone continue to describe the recent swarm activity using careful, measured language, unusual against the historical baseline, worth continued close attention, and not, as of the most recent public updates, associated with any elevated volcanic hazard. The alert level remains at its lowest setting. Ground deformation continues within its normal range of seasonal and long-term variation. Gas chemistry sampled from monitored vents continues to reflect typical hydrothermal behavior rather than any sign of magma migrating toward the surface. Every additional week of data collected adds another small piece to the picture, and so far, every piece continues to fit comfortably within the much larger, decades-long puzzle researchers have been carefully assembling about how this particular system behaves. What continues to genuinely interest scientists, and what will likely continue to be studied and discussed for months to come, is not whether Yellowstone is approaching some dramatic, imminent event, The evidence simply does not point in that direction. What interests them is the more subtle, more scientifically valuable question of exactly what process is producing this particular unusual pattern of swarm behavior, whether it eventually turns out to be an unusually large but still ordinary hydrothermal readjustment, similar in nature to the swarms recorded in 2010 and 2017, or whether it represents some new, previously undocumented category of behavior within this specific system's deep plumbing. Something that would itself be a genuinely significant scientific finding, expanding our understanding of exactly how systems like this actually work, entirely separate from any question of danger. This is, in many ways, the quiet, patient heart of what real scientific curiosity actually looks like. A willingness to sit with a genuine unknown, to keep gathering careful evidence, to resist the temptation to force an answer before the data has earned one, and to find the process of narrowing that uncertainty deeply satisfying in its own right, regardless of how dramatic or undramatic the eventual answer turns out to be. The researchers watching this system tonight are not hopping for an eruption, and they are not bracing for one either. They are simply doing the same patient, careful work they have always done, adding each new piece of information to an already enormous, decades-deep foundation of understanding, one quiet measurement at a time. And there is something worth carrying with you into whatever rest follows this long evening together, about what that patient watching actually represents. Somewhere in Wyoming right now, sensors buried deep in frozen ground are recording every tiny tremor passing through the rock above an ancient reservoir of heat that has been rising from the same patch of mantle for millions of years. Satellites are quietly passing overhead, comparing this week's measurements against last week's, against last year's, against decades of accumulated history, watching for the smallest possible shift in elevation across a landscape most people will only ever know through a handful of photographs from a single family trip. Somewhere, a researcher is looking at a fresh batch of gas samples collected from a steaming vent earlier that same day, checking its chemistry against a long, careful baseline, adding one more small, unremarkable, deeply important data point to a study that may not reach any final conclusion for months or years yet to come. None of that work happens quickly. None of it happens dramatically. It happens the way most real scientific understanding actually happens, slowly, patiently, one careful measurement layered gently on top of the last, until eventually, sometimes after a very long wait, a clear picture finally emerges from what once looked like nothing more than noise and uncertainty. That is precisely the stage this particular story sits at tonight, still unfolding, still being gathered, still resting comfortably within the range of what a living, ancient, deeply monitored volcanic system is expected to do as it continues its own slow, patient breathing beneath a landscape that will still be sitting there, steaming quietly, long after all of us are gone. If you take one thing from this evening's journey through the ground beneath Yellowstone, let it be this: uncertainty is not the same thing as danger. A system behaving in a way that is genuinely unusual, genuinely worth careful scientific attention, is not automatically a system approaching disaster. Sometimes it simply means a very old, very patient landscape is doing what it has always done, shifting and adjusting, and occasionally surprising even the people who understand it best, while remaining, in every measurable way currently available to science, well within the range of its own long, quiet history. It is worth letting your mind settle, for these last few minutes together, on the sheer patience embedded in a story like this one. Nothing about Yellowstone moves quickly. Its magma reservoir formed over millions of years. Its calderas are separated by intervals measured in hundreds of thousands of years. Even its faster surface changes, a geyser shifting its schedule, a hot spring changing color, a swarm of small earthquakes rising and falling over the course of weeks, unfold on a timescale that dwarfs anything resembling the pace of an ordinary human life. There is something quietly comforting in placing yourself, just for tonight, inside a timescale this vast, letting the small, sharp urgency of your own day dissolve gently against the backdrop of something that measures its changes in millennia rather than hours. The ground continues its ancient, unhurried rhythm tonight, exactly as it has for longer than any record exists to describe it, and exactly as it almost certainly will continue to, long after tonight ends, long after this particular swarm of earthquakes eventually settles back into quiet, long after the researchers currently studying it have long since retired and been replaced by new ones, inheriting the same patient work, the same careful instruments, the same quiet dedication to listening closely to a landscape that has never been in any hurry to explain itself all at once. It is worth taking a few extra minutes here, before we let this story rest completely, to talk honestly about what it would actually look like if this system ever did begin moving towards something genuinely different, because understanding that picture clearly is, in its own way, one of the most reassuring parts of this entire story. Volcanic systems capable of the kind of large eruptions Yellowstone has produced in its deep past do not skip from quiet background behavior directly to catastrophic eruption without warning. Every well-documented major eruption in the geological record, studied through careful analysis of the rock layers and mineral crystals left behind, shows clear evidence of an extended period of escalating unrest beforehand, unfolding over months, years, in some cases even decades, not hours or days. That escalation would show up unmistakably across every one of the monitoring layers we discussed earlier, not just one isolated signal, but a genuine, sustained alignment across all of them together. Ground deformation would need to show significant, accelerating uplift, not the gentle, seasonal rise and fall currently being recorded, but a clear, sustained trend concentrated specifically above the shallow magma chamber, growing more pronounced over consecutive months rather than fluctuating within a normal range. Seismic activity would need to show a genuine, sustained increase in both frequency and intensity, accompanied by earthquakes originating from progressively shallower depths over time, a clear signature of material actively moving upward through the crust, rather than simply readjusting within existing fracture networks. Gas emissions would need to show the specific escalating sequence associated with magma approaching the surface, a shift toward higher temperature, higher sulfur content gases, replacing the more typical carbon dioxide-dominated emissions currently being recorded. None of these signals exist in isolation as reliable warnings on their own, which is exactly why researchers insist on requiring genuine convergence across multiple independent measurement systems before treating any pattern as a sign of true escalation. And critically, this kind of convergent escalation, if it ever began, would almost certainly unfold slowly enough, over a long enough stretch of time, to give researchers, and by extension the public, meaningful advance warning, likely measured in months at an absolute minimum, quite possibly considerably longer. Based on everything understood from studying similar systems and their documented pre-eruption histories elsewhere in the world. This is precisely why the monitoring network exists in the form it currently does: dense, continuous, cross-checked across multiple independent methods, specifically designed to catch exactly this kind of gradual escalation as early as scientifically possible, long before it would ever become an immediate concern for anyone living in or visiting the region. Emergency planning agencies in the surrounding states maintain response plans built around this understanding, developed in direct collaboration with the same scientists studying the volcanic system itself, precisely because everyone involved understands that any genuine future escalation would be a slow, carefully tracked process, not a sudden, unannounced surprise. Knowing this changes how a story like tonight's deserves to be held in your mind. The current unusual swarm activity is being watched by people whose entire professional purpose is to notice exactly this kind of change, evaluate it against exactly this kind of well-defined, well-understood escalation pathway, and so far, measured against every marker along that pathway, the system has not moved meaningfully beyond its normal, dynamic, background behavior. That is not a guess or a comforting story told to ease anxiety. It is the direct, current output of one of the most thorough volcanic monitoring efforts anywhere on the planet, built specifically, deliberately, patiently, to answer exactly this question with real evidence. And real evidence continues to say tonight that this remains a system breathing quietly within its own long, ancient rhythm. There is a particular kind of quiet gratitude worth feeling toward the people who choose to spend entire careers on work like this, watching a landscape that rarely rewards them with anything dramatic, gathering years of careful measurements that most often simply confirm, again and again, that everything remains within its expected range. That is not a small kind of work, even though it rarely makes headlines of its own. It is the slow, patient maintenance of genuine understanding, the kind that only becomes visible in the rare moment something actually does begin to shift, and only because someone was paying close, careful attention long before that moment ever arrived. Tonight, that attention continues exactly as it always has, unremarkable, unhurried, and quietly essential, long after most of us have already drifted off to sleep, trusting, without needing to think about it very often, that somewhere out there, someone is still listening carefully to the ground. Thank you for spending this long, slow evening with us here at Pale Blue Drift, walking together through deep time, through careful instruments, through the patient, unglamorous work of real scientific understanding, all the way from a single unusual swarm of earthquakes down to the ancient, breathing heart of a landscape most people only ever think about as a place to see geysers and wildlife. If this kind of slow, careful journey through the quiet mechanics of our world is something you would like to return to, there will be more evenings like this one waiting for you, more distant worlds, more patient mysteries closer to home, more long, unhurried stories built specifically for exactly this kind of stillness. For now, let the rest of tonight be simple. Let your breathing continue slowing, the way it likely already has without you fully noticing. Let the ground beneath wherever you happen to be resting hold its own quiet, ancient patience, unrelated to anything happening thousands of miles away in a wilderness you may never visit, and yet somehow, in its own way, part of the very same enormous, unhurried planet you belong to. Whatever tomorrow brings, it can wait quietly until morning. Tonight, there is nothing left to do but rest. Good night.